Welcome to an instructional video on how to perform tensile testing for our course. We are going to use a Pasco materials testing machine, ME8236, with various samples to perform this laboratory exercise. To get started, what we will do is create a folder for our team to collect data. So we will put this folder in this other folder here. We might call it Team Rutgers 230926 for the date, and we open it up and there's of course nothing in it, and we come up to the desktop and we find that there's this MechMat tensile testing template. We're going to copy this, don't drag it, just copy it into this folder, and probably not a bad idea to go ahead and rename this file as well. This file is a Pasco capstone file that will allow us to collect data for our tensile testing experiments. The next thing we do is we come over and we look for an appropriate sample. We're going to use one of the aluminum samples, which should be available in a bin. Okay? And they're painted white. I'm not quite sure why, but they are. And these are the ones we're going to be using. Before we put the sample in the machine, it is a good idea to measure its dimensions. And which dimensions would be appropriate here? Well, we're going to be looking at stress-strain curves. So we would like to know some of the parameters that we use for collecting the data for stress and strain. So for stress, we would like to know the cross-sectional area. And for that, we can go ahead and measure it. So the thickness comes out to be 0.63 there, 0.63 there, 0.63 there, 0.62, and so we'll just go ahead and say it's about 0.6 millimeters, okay, given the accuracy of our potential measurements. So 0.6 millimeters in thickness, and then in width, when we do this measurement, 6.06, 6.06, 6.06, or 6.05. We'll go ahead and we'll say it's 6 millimeters. So 0.6 millimeters thick and 6 millimeters wide. Please make sure you measure it yourself using the calipers that you'll find in the lab. Those are the cross-sectional area is important for stress, and for strain, we're going to want to know something about the change in length divided by the gauge length, or the initial length of the sample. Now, we don't measure the entire length of the sample. We measure the length where it is narrow. Okay, so we can estimate when we look at this curve a little bit here into this dog bone specimen, and we'll say, yeah, it's about 56 millimeters. Okay, so we've got 6 millimeters wide, 0.6 millimeters thick, and 56 millimeters long. We'll then come over here and we'll bring our sample into the tensile testing machine grips. Now, these grips are already in place. These are the larger grips. And to put these in, I guess I'll show you. The upper one, labeled upper, can be placed by pushing up and then using this bolt at the top. And you want to make sure that it can still spin freely in that degree of freedom. The bottom one is put in place by spinning the grip onto the lower cell, as we see here. Okay, so I'm going to lower it back down. And again, on the bottom, we also, there we go. Yeah, we also want to make sure that we have an appropriate rotational degree of freedom here. So we'll be very loose in that direction. Now, we can put their sample in here, and we want to get the grips over the larger ends of the sample. So I'm actually going to move this down a little bit so that we kind of see most of the ends disappear in the grips. Now we haven't tightened the grips yet, but this will just ensure that we've got plenty of surface area for the grips to clamp. And initially I'll just finger tighten the top grip. Oops, and that's a little bit off-centered, so now a little tricky. We'll get the this one there, and the bottom one here. Okay, I want it to be more or less centered and vertical. Both of these grips. Now we can use this Allen wrench tool. So, and go ahead and screw in the 4 outer bolts on these grips. And the staff here have done a great job of making these custom grips that clamp and use a little bit of taping action to ensure that it doesn't slip on these particular samples when we're applying the tensile load. And we can tighten these until it doesn't really turn anymore. Okay? Don't be too scared of applying too much torque. We come over here and we've got the data acquisition software open in this template. And what we see is a table that's empty with position versus and force. And then over here we have force on the y-axis, position on the x-axis, and we also see that we have a meter to give us the speed at which we are pulling the head or lifting the head away from the base. So that's the rate of extension. So to get us started, we can go ahead and hit record, and what we'll see is that there are data that come in, and they might be slightly negative, but they might be close to 0, maybe even slightly positive. But we just want to kind of start to initiate. Oh, okay, we saw a sudden jump. So I'm going to come back down, and we're going to keep it about there, and that will probably be, a pretty good starting point for taking the stress strain data. So we'll stop the collection of the data, and that is considered our quote first run. So that was run number 1. We don't want to delete it. We don't need to delete it. We don't really need to keep it either, but we'll just leave it there for now. And then we're going to take another run, and in this run we're going to collect the data for our stress strain curve, which will come from force versus position. So we'll hit record, and then I'm going to kind of gradually try to go at an even rate, trying to keep it going kind of even, okay? And then we see, wow, look, it leveled off. Now this is not stress, but this is force, and force is, of course, proportional to the stress. And we see that we're kind of in this plastic regime. Okay, we're going, and 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 we're going, we're still going. Okay, maybe it's starting to go down a little bit. Okay, and we're probably gonna, there we go. And we've broken, all right? Now something that I should have done before, and that you will do in your experiments, I realized after we were going, is place these shields that Velcro onto the sample, like so, okay? So please make sure you do that for your tensile test. Now, let's go ahead and collect the data. Oh, we should stop this, it's still going. Collect the data and begin processing it to get an idea of what happened. So we can leave this here for now. And to facilitate the processing, we'll go and use a Colab script. So go to the website and come all the way down to the bottom of, or not the bottom I guess, but below all the sessions for the course, and click on this MechMat tensile testing page. And here is Colab. So I'm going to open this in a new tab. Okay. And in addition, I'm also going to take down this PowerPoint file, okay, that I can use to collect data. It's just an option. I'm actually going to go ahead and download it. I guess I don't have to. I can just leave it. I'm going to need to sign in because it's in view only mode. So maybe I'll go ahead and download it. Either way, right? But I can copy and paste my data into this. Whoops, into this folder. Okay. And if I don't have PowerPoint on this computer, which is possible, okay, then I can go ahead and I'm going to be, I guess, need to sign in here. Okay, so what are we going to do? Well, we are going to first make this a little bit more legible. We're going to bring in the file and that we just created after we export it. So we come over here to File and we export the data, and we only really need run number 2. Okay, so we'll just select run number 2 here. You can also deselect all and then select run number 2 if you so like. And we're going to do it in a comma separated values file. And we're going to export to file. And in this case, I'm going to export it to my folder. And this will just say this is aluminum test 1. Okay. And then we come back into Python. And we're going to run the first cell. Now, what's interesting here, okay, fine, is that when we run this first cell, it's going to keep spinning even longer than normal. Okay, see this? And then it comes up with this browse for files or no files selected. So what are we going to do? We're going to go into the folder where we just took our data and look for the CSV file. We're going to hit open. It's going to bring it in. Okay. And then we're going to look at the file name. So it's called aluminum test1.csv. If you load it a couple of times, it will add parentheses. It's very important that the right word here, like on the right here, is what we put and copy and paste here for name. All right. Then we run that one. Okay, I hit Control Enter, but you can hit the play button instead. We come down and what we see is a list or an array, or the beginning of the array for the data that were collected in this file. We can then come down to this, so we ran it, and so we're pretty confident we have the data in, and then we can go ahead and hit this play button, and it's going to play the data that we collected. Okay, and it plays it with, maybe I'll just back up just one little thing here so we can kind of see the whole plot. All right. It plots the data in different colors with different values for the y-axis, and it's not really thinking too much about trying to make all these colors the same on this graph or the same height. What we see here is that green corresponds to force, and we see that we had the largest values of force compared to time, position, and speed. And if we go back to the data that we collected in Pascal, we see that, okay, it was going up to maybe 1,500 newtons. So that is comparable to what we're seeing here. What's important to keep in mind is the x-axis, which essentially is telling us the index of the data that were collected. So, for example, if we come back here, you see that the data have been indexed. So 1, 2, 3, 4, 5, right? So we see all these numbers here, and then we see force and position values associated with these numbers. And it's sampling at 50 hertz. So it's a reasonable number of points that we've collected. In this case, almost 4,000 points. Okay? So what we want to do for different parts of this script is realize, okay, where did the data that we're interested in start with respect to an index, and where did it end with respect to an index? And so there's a little bit of trial and error here in terms of what you pick, but let's say that it started, maybe we'll say, okay, 20 it started at, and let's say that it ended for the whole stress strain curve, let's say we ended about 2250. All right, so what we're going to do is that we're going to create our starting index, and this is to create the entire stress strain curve. So what did I say, 2250? Just kind of as an estimate, 2250, and then 20. So let's see what we get when we plot this. All right, so we'll hit this button. Oh, okay, right. Good, I'm glad that happened. So what we also need to do is change the name. We don't have a run number 1, but we do have a run number 2. So we have to change the names of the columns that we're taking from that file. So now let's run it again. Okay. And if we wanted, we could change this sample number thing. We could say, oh, I'm going to call it aluminum number 1, just, to add some further clarification. And this is force versus position. And that guess of 25 looks like it was pretty good. Depending on what I'm trying to capture, okay, this guess of 2250 also looked pretty good too. So we'll go ahead and keep these, all right, as they are. And then we'll allow the script to plot stress and strain. Now, how do we plot this? We need to know the cross-sectional area, we need to know the length, right? So it's important here that we go ahead and we remember what we measured, and we put those values in. So we said it was 0.006, 6 millimeters for the width, and we're gonna say it's 0.6 millimeters for the thickness, all right? So this is 6 millimeters for the width, this is 0.6 millimeters for the thickness, and I think we said it was something like 56 millimeters long, okay? So those are the values we put in for the cross-sectional area and the initial length to allow the computer then to tell us or to plot an appropriate stress strain curve. Okay, so then we go ahead and we run this, and what are we going to see? Oh, again, we could change aluminum. We could change the sample to aluminum number 1 if we want here. Not necessary, but there we go. Okay, and what do we see? Well, we see stress strain curve. We see it goes up a little bit beyond 400 megapascals. This is the elastic region. We'll talk about that more in a second. And then it comes off and comes over. Just like we saw with the force and position curve. We also see values of strain here on this axis. And there is significant strain, right? This is 1% strain. That's quite a, that's, I guess, normal, you could say, but it goes on to something like 7%, 7.5% before it breaks. That's quite a bit of strain. We see that it calculates the modulus of toughness for us by using the trapezoidal method to calculate the area under this curve, and it estimates the ultimate tensile strength as the max. So somewhere around here we got maybe to 430 megapascals, all right? So these data are relevant to the questions in the lab or that we have to fill out, or that you get asked to fill out. So what I'm actually going to do is a couple of things. One, I'm going to take a screenshot and I'm going to put it in my PowerPoint or my Google presentation folder. Okay, so I'm going to do this like this. Okay, and I'm going to go ahead and keep it there, and I'm going to see if I can paste it in here. So the first question is actually asking about what is the ultimate tensile strength. So I'm going to paste my image in here. Okay, got it. It's under view only. I thought I had it signed in. Maybe I better make a copy. Entire presentation. That's fine for now. I'll keep it over here. It's loading it in. Okay, I like this. It's a space. All right, and I have it just like that. The other thing you can do in Colab to keep track of things nicely and to get maybe a higher definition plot is to go ahead and do a save image as. So I'm going to bring this into my folder, and we're going to call this aluminum test 1, and I'll call it complete stress strain curve. And you'd be like, wow, this is really tedious. Well, this is a little bit tedious. It's also very similar to what you do as an experimentalist for research, right? We had to keep track of our data. When I was a grad student, I kept a lot of data in PowerPoint files. People can argue about how we might store or keep logs of data most effectively. And I'm not saying that you have to use PowerPoint, but it can be a useful tool. So we're going to bring in, we're going to insert, image and upload from computer. We'll go into here, and we'll go ahead and insert this. So this is now a screenshot on the left, and the pasting or the inserting of an image that was exported from Colab. So I'd argue this is a little more pure on the right. The next question was, what is the modulus of toughness? Well, the script also gave us that information up here, okay? And so we can place that information and enter it into Canvas. Okay, now the next question is about figuring out the elastic modulus, okay? And how do we go about doing that? Well, we're going to use the script to help us with this calculation, but we want to feed it the appropriate data. So this script is asking us to select the region of elasticity, all right? And so we can use the same starting index that we used previously. So what did we use previously? We said up here we could use 20, all right? But now we need to essentially cut things off closer to the proportional limit, or the yield strength, or the elastic limit, okay? And so where does that more or less happen? We go back to this plot, and we'll say, let's just estimate it at around 300 for starters, okay? So we're gonna go from 20 to 300. So I'm gonna put in the start index as 20, and I'll put in this index as 300. And then we'll plot and see what we get. Okay? And what do we get? We get something that looks kind of like this. We see the data, and we see just a straight line, and that's what we're going for. If we go a little bit further, let's just go a little bit further. What do we see here? We still see a pretty straight line. Maybe we can go a little bit further even. 400. Okay, it's starting to curve off. Okay, just like this. All right, so where we decide to choose our data affects things a little bit. The estimated yield strength that is calculated is actually based on the maximum. So let's just go somewhere in between. We'll say like, I don't know, 380 maybe. So that's not too bad. We could go lower if we're really interested in the elastic limit. All right, maybe we should go 350. Okay, yeah, that's pretty good. All right. So if you were looking here, you also saw that these numbers changed slightly. Okay, and the elastic modulus that we're getting from the fit to ease data with the measurements we took is about 80. Okay, now that's a little bit high because we know that the elastic modulus for aluminum should be around 70. And there can be various reasons why our measurement is off. When I say 70 gigapascals to be more specific. Okay, and I'm going to go ahead and put this copy and pasted image in, okay, as we see here. And I'm also going to go ahead and do the same thing I did previously with saving the image. Okay, so this is aluminum test 1 elastic. Okay, and I can once again bring, well, where did it go? Did it go into downloads? No, hopefully it went into the appropriate folder. Okay. Yes, there, that's it. So I can go ahead and I can import or I can insert this image from the computer like that. Okay. And so in Canvas, your job, your opportunity is to continue going through and taking measurements of the tensile test specimens, and then you get to do a design problem in a little bit as well. Now, when you do the aluminum and steel samples for this lab, you will go ahead and use the larger grips. Okay, so the ones that we already have in place here. Or the ones that you see, oh, it's pretty tight. But when it's time to move to the paper samples, what you're going to do, and you can see it's kind of nice. It's got a little bit of marking from where the teeth were into it. Pull this out. Okay, great. These are good. These are great. Okay, and then for the paper-based samples, we're going to use a different set of grips. Okay, we're going to use the smaller grips. So this is a paper-based sample that we cut on a laser paper, and these two grips out. Now, you could test this sample here, and these grips, tends to lead to tearing with one single piece of paper. If you put multiple pieces of paper together, then you'll have a little more success. Or you can use these nice grips provided by Pasco that are smaller and do a very nice job of clamping this thinner substrate. Put it in similarly. Yep, okay, that's too much. I want to make sure I have that degree of freedom of rotation at the top. Put this at the bottom, like so. We should be off. Well, not off and running. We have to put the sample in first. So you can kind of see that this goes in. I'm going to do the bottom one first so I can see better. Yeah, okay, so that goes in nicely. Finger tighten. Okay, and then I got to bring it down. And don't worry too much about flexing the paper. You don't want to crease it, but it's okay if it bends elastically, as you might say. this sample, we can use this other wrench driver tighten grips on this piece of paper. Okay. And what I forgot to do last time, we can do appropriately here. These shields in place. And then we can perform our tensile testing experiment. Before placing this sample in there, you may want to measure the dimensions of this piece of paper so that we can calculate the stress appropriately. And we then have some more questions. And there will be an opportunity also to look at what we call the anti-dog bone. So there are scissors, so we'll characterize the properties of this material, and then we have a challenge problem or a design problem where we can take different implements. That's just a fancy way of saying scissors. All right, we can take some scissors and we can cut out portions of this anti-dog bone, as we'll call it, to be able to design for a specific force that our anti-dog bone will end up being able to handle. Okay? And so first we characterize the ultimate tensile strength of this material, and then we use that information to understand how we can design a sheet to withstand a specified force, okay, based on understanding what the ultimate tensile strength is. And maybe we should design for the yield strength instead. It's going to, when you take the tensile test data for the paper, you might see some interesting behavior. So it's going to be approximate in either case. This concludes our instructional video, and I hope you enjoy the experiment. Thank you for watching.